This is a video for AQA Discrete Mathematics. This is Graphs and Networks section 2.3, where we're looking at the lower bound for travelling salesperson problem. Well, from the outset, I'd like you to understand that as a lower bound, we won't necessarily be finding a Hamiltonian cycle. In other words, it's not a solution to the problem. However, it is a number that we can be sure is less than the optimal value. So what would we like our lower bound to do? Well, certainly we need something which is easy to find so that we can do it efficiently, and presumably we'd like it also to be easily programmed so that a computer can do it for us. The start and end vertex should be the same, and to make sure that we've got a number which is less than our optimal tour, then we're going to add in that start vertex using the smallest pair of arcs that we can. We also need something which then is connecting all of the other points together, all the other nodes. So something which does this is a minimum spanning tree. So let's say our minimum spanning tree might look something like this. Now if we add those two things in, so our smallest arcs might join in like this, you can see that there we haven't produced a Hamiltonian cycle, but we'll see that that must give us a total which is less than the optimal tour itself. So let's just go through that again. So to get the lower bound, we start off by ignoring, in fact, one of the nodes. Doesn't matter which one, that can be selected at random, or we can go through systematically and look at them all one at a time. So we ignore that and the edges that are joining it to all the other vertices. For the other vertices, what are called the residual set, we find the minimum connector, or minimum spanning tree. Now that you can do sometimes for a small network by inspection, but we've also got the algorithms, of course, Kruskal's algorithm and Prim's algorithm that we could use. So there we are, we've found our minimum spanning tree for the residual set of vertices, and now we add in the one that we took out at the beginning with the smallest arcs. And there we add up all those numbers, and that must necessarily be smaller than the optimal tour. It's not a tour, as you see, but let's imagine that in fact that minimum spanning tree happened by chance to be just a line like that, and then that would have produced a tour, and it must, because it's the smallest, the minimum spanning tree, and we've got the smallest arcs joining in, that would have produced a Hamiltonian cycle. Very unlikely that it happens, but you can see therefore why our method produces a number which is less than or equal to the optimal tour. If it happens to be a cycle, a Hamiltonian cycle, then it must also be an upper bound. Therefore we've got an upper bound and a lower bound which are exactly the same value, hence it must be the optimum solution. Well, now let's look at an example where we're on a small network of 5 nodes. You see, this is a complete graph. So what we're going to do is to start off by deleting A. So we're going to have, starting at A, the first thing we do is imagine that A is not there, and then we look at the other points, the other nodes, and find the minimum spanning tree. As I say, we can do this by using one of the algorithms. So we can see that from the smallest arc there is 7, then the next one is 8, and then the next one 9. So there we have a minimum spanning tree for the residual set. And now we add in the smallest arcs from A, which are the 9 and the 8. So we have therefore a minimum spanning tree for the residual set, so something we call it a residual minimum spanning tree of size 7 plus 8 plus 9, so that's 24, and therefore the lower bound solution is our 24 plus those two smallest arcs of 8 plus 9, giving a total of 41. Let's see what happens now if we start at D this time. So if we start at D, we imagine that one's been removed, and we look at the minimum spanning tree for the other set. There's a 7, an 8 and a 9. There's the minimum spanning tree for the residual set. And then we add in this time the 10 and the 8 are being added in to give us our smallest arcs. So the minimum spanning tree this time was 7 plus 8 plus 9. Again 24, but this gives us a lower bound of 24 plus 8 plus 10. So this time a lower bound of 42. Now, if you had the choice, which ones would you use? The first one, which were from A, was 41, and the second one from D is 42. I'm hoping you'd say, well, it's a lower bound I'm looking for, therefore I need the largest of those. So far we'd say that 42 is our best lower bound. So there we are, there's the system again. Choose a vertex, delete it and all its edges. We find a minimum connector for the remaining, and then add the vertex back in using the two smallest weighted edges. We do that for different vertices and choose the largest value that we get. Now, so what you could do is to practice looking at maybe the other vertices, E and C. So pause for a minute, try a few yourselves, of the starting by deleting, for example, vertex C or B or E, the ones that we haven't tried, and see what answers you get from that. Right, there are the solutions. Now you can see therefore that our largest lower bound is 45. So if our largest 45, that means that the optimal solution is greater than or equal to 45. We haven't actually checked if any of these are cycles, but we can say that the optimal tour is bound to be greater than, or possibly, very unlikely, but possibly equal to the 45. Now our solutions, we said, are not Hamiltonian cycles, so therefore we can't consider this also being an upper bound. So what do we know so far? Well, from the upper bound video, if you've looked at that, we found that the upper bound had a value of 48, and we've now found a lower bound with a value of 45. So because none of these were Hamiltonian cycles, we could say that 45 is less than or equal to the optimum is less than or equal to 48. It's possible for us to do exactly the same thing, but this time using a matrix. So if we're starting at A, for example, we would first of all remove A, so the rows for A, or ignore them, and work on the rest of the matrix, the residual matrix, and using one of the algorithms. So here's our residual matrix. So we'd go through that, for example, using Prim's algorithm. So we could start off using Prim's at B, so starting off with B as number 1, that would give us the 2 there. Remember that we then delete the rows for B and C. We label C with number 2. So we're now looking at both columns. So remember, this is not the nearest neighbour algorithm, we're using prims, so we're looking at both columns 1 and 2 now. So that smallest there is number 1, which produces D, which comes in as number 3. So we cross off D. We've now got all 3 columns to look at. So let's take the 2 there at F. So F becomes the 4th column. And then finally, that will give us the E there. So that gives us a minimum spanning tree equal to 2 plus 2 plus 1 plus 1. So a minimum spanning tree of 6. And then we have to add back in the A. So let's look at that. So there's our original matrix back, and we've got to add back in A with the 2 smallest, and you can see those are 1 and 3. So our lower bound solution for this particular network would be 2 plus 1 plus 2 plus 1, which is the minimum spanning tree, plus the 3 plus the 1, giving us a total of 10. Well, that's the end of our video for finding a lower bound. In the final video in this section, we'll be looking at practical problems as opposed to the classical problem that we've been looking at where we had complete networks. In the practical problems, we're looking at when the network is not complete.